Hello friends, it's a beautiful morning in Kigali and IBM is here with another episode of Learning Physics with me, and I hope we should move to part 2 of medical physics. Remember I said this unit is going to involve um, past paper questions from X-ray scan, from a CT scan, from uh, PET scan. So you should now be prepared to get understanding or to actually try to understand how these questions are going to be examined. If this is your first time to see past paper questions or paper 4, you should now be prepared to answer questions under ultrasound scan, X-ray scan, the CT scan, and the PET scan. This unit entirely comprises of many parts which require a lot of reading, and as an A-level student, reading should be part of you. Of course, if there are calculations, the calculations are easy, and I'm trying my level best to simplify these calculations so that we get confidence with them. So let's move to the document. We stopped, I think, on page 200, 500 and we stopped on page 529, and I want us to start from there straight away. Okay, so right from there, by reference to ultrasound wave, an ultrasound wave, explain what is meant by specific acoustic impedance. At this point, you should now be confident with what we mean by a specific acoustic impedance. That is the product of the density of the medium, and the speed of the ultrasound wave in the medium. So if next time they assign these 3 marks, you can even add acoustic impedance Z is equal to the density times C. That is the acoustic impedance, the product of the density of the medium and the speed of the ultrasound wave in the medium. Okay, so an ultrasound wave is incident normal on the boundary between two media. The media have a specific acoustic impedances Z1 and Z2. State how the ratio intensity of ultrasound reflected from boundary over the intensity of ultrasound incident on the boundary depends on the relative magnitudes of Z1 and Z2. So remember, intensity reflected over intensity incident is what we call the intensity reflection coefficient. That is alpha, which is actually going to be Z2 minus Z1 over Z2 plus Z1, and this is squared. So we note from that expression that if Z2 is much greater than Z1, what does that mean? Z2 is much greater than Z1. It means when I substitute the value for Z2 and Z1 and I subtract, I approximate get Z2. When I add, I approximate get Z2. That means this will be the approximate Z2 over Z2, and this is squared, which is approximately 1. So it means the ratio is going to be approximately 1. So we can say then the ratio is approximately equals to 1. And what does this imply? If the ratio alpha is approximately equal to 1, then this means more reflection. Remember, it is the intensity reflected over the incident intensity. So this one means more reflection, less transmission. More reflection, little transmission. More reflection, little transmission. So it means more ultrasound is reflected at the boundary, and there is very little transmission across the boundary. That is condition number one. How about if Z2 is now very close to Z1, approximately equal to Z1? If Z2 and Z1 are approximately the same, that means when I subtract them, I get approximately 0. That means in the numerator I have 0. Of course, in the denominator it's not 0. If Z2 is approximately equal to Z1, the difference is approximately 0, which makes alpha to be 0. Remember, alpha is intensity reflected over incident intensity. So this means that the ratio is approximately 0. The ratio is approximately, I don't want to write approximately, I'll just write the ratio is close to 0. That's what it means. When the ratio is close to 0, it means almost there is no reflection. So we can say little reflection, and it is mostly transmission. So there is very little reflection and it is mostly transmission. State what is meant by attenuation of an ultrasound. What is to attenuate? To attenuate is like to reduce. So attenuation of an ultrasound wave is like the loss or reduction in intensity or power of the ultrasound wave as it passes through a medium. So the loss of intensity, or power of the wave as it passes through a medium. The loss of intensity or power of the wave or the ultrasound wave as it passes through a medium, that is attenuation. A parallel beam of ultrasound is passing through a medium. The incident intensity I naught is reduced to 0.35 I naught. So the intensity transmitted, therefore, is going to be that one on passing through a thickness of 0.046 meters of the medium. Calculate the linear attenuation coefficient mu of the ultrasound beam in the medium. So intensity transmitted is equal to I naught e power negative mu times x. So we want to find mu, we just substitute. The intensity transmitted is 0.35 times I naught. The incident intensity is I naught e power negative mu times x, which is 0.046. So I naught has cancelled. I introduce natural logarithm. I naught has cancelled out because it is on both sides. So we shall have that ln of 0.35, which is negative. When I find ln of E, I only remain with the power. So this would be negative mu times 0.046. So I now find mu. You can now find mu, which is ln of 0.35 divided by negative 0.046. You press your calculator. So from my calculator, I am getting 23. From my calculator, I'm getting 23 to two significant figures. Okay, you can also verify. Number next, by reference to specific acoustic impedance, that is Z, the Z values, explaining why there is very little transmission of ultrasound waves from air to skin. What do we know about air to skin? If you are very careful, if you have seen the past paper questions that we have already answered, for air it is approximately 430 Z, and for skin is around 1.6 times 10 power 6 Z value. That means there is a very great difference between air and skin as far as acoustic impedances are concerned. Yet you remember the intensity reflection coefficient alpha depends on the difference between the Z values. If the difference is much larger, there is more reflection other than transmission. So there's a very much difference between Z for air and Z for skin. So we expect much reflection than transmission. So we can say the intensity reflection depends on the difference between the acoustic impedances. The intensity reflection coefficient depends on the difference between acoustic impedances. So the intensity reflection coefficient depends on the difference between acoustic impedances. Note that the specific acoustic impedance of the skin is much greater than that of air. The specific acoustic impedance of the skin is much, this is very important, much, so that there is emphasis, is much greater than that of air. Therefore, most ultrasound is reflected and very little transmission occurs. Most ultrasound is reflected and very little transmission occurs. So that is the simple explanation, which I expect to give you the 3 marks. The intensity reflection coefficient depends on the difference on the Z values, as we see in that equation above. And the specific acoustic impedance of the skin is much greater than that of the air. That means the difference is very large, giving us approximately Z2. And Z2 divided by Z2, this will give us approximately 1. So most ultrasound is going to be reflected and there will be very little transmission. Okay, a simple mode of one section of a CT scan is shown in the figure here. So we are now mixing up questions with those of CT scan. So you have A, B, C, D. The model consists of voxels. Remember, a voxel is a small volume element. We said during a CT scan, the body is divided into smaller sections. The section is also divided into smaller volume elements, which we call the voxels. And each voxel is assigned a number, which we call the pixel, which corresponded to the intensity of the the X-rays, which go through that part of the body or that specific voxel. So in this model, the voxels are viewed in two in turn along 4 different directions, D1, D2, D3, and D4 as shown here. The pixel readings in each of the 4 directions are noted. So they noted all the pixel readings in the 4 directions. And the total reading for any one direction is 19. If you remember from your study of CT scan, the total pixel readings is what we call the background intensity or the background radiation, which must always be removed from the total readings in the process of reproducing the pixels. The pixel readings for all the directions are summed to give the pattern of the readings shown here. So these are the pixel readings of all the 4 directions. This is the pixel total. Okay, state the background reading in this model. We have seen that the sum of the detector readings in any one direction was 19. And I say that this is the background intensity or the background reading. So the background reading is 19. Determine each of the pixel readings A, B, D, C. So remember, first of all, we subtract the background intensity. And after subtracting the background intensity, we take allowance of the fact that more than one view was taken. So I will redraw the same table above. And I just want to show the working because it is 4 marks. So I will subtract. I will have 25. I subtract the background intensity, which is 19. I have 34 minus the background intensity, which is 19. 28 minus the background intensity, which is 19. And 46 minus the background intensity, which is 19. Then I take allowance of the fact that more than one view was taken, and that is there are 3 more views which were taken. So I divide this by 3, divide by 3, divide by 3, divide by 3. So you can check your calculator. 25 minus 19, divide by 3, 34 minus 19, divide by 3, 28 minus 19, divide by 3, 46 minus 19, divide by 3. So from my calculator, I am getting A, which is this part 25 minus 19 over 3, I'm getting it as 2. And B, which is 34 minus 19 over 3, I'm getting it as 5. And D, which is 28 minus 19 over 3, I'm getting this as 3. And C, which is 46 minus 19 divided by 3, I'm getting this as 9. So those are the original pixel readings that we had before moving around in the 4 directions. Use your answer in B to determine the pixel readings along D3. Let's see D3. Where is D3? So D3 is from the top. D3 is from the top. D3 is from the top. So D3 is from the top. So the detector is this side down here. Remember, we sum up the pixels. So this one will be 2 minus 3, which is 5. And 5 plus 2 plus 3, which is 5. And 5 plus 9, which is going to be 14. So the detector readings, determine the pixel readings along the direction D3. So that is going to be 5 and 14. So those are the detector readings. That is A plus D and B plus C. Then use your answer again to determine the pixel readings along the direction D4. I think D4 was in this side here. This was D4. So the detector is going to be this side. So we sum up the readings diagonally. I'll change the color here. So we sum up the readings from this side. So this is what we shall be having. Therefore, we shall sum 2 will not be summed up with anything. So that is 2. 5 sums up with 3. So we have 2 8, and 9. So the detector readings will be 2, 8, and 9 from that particular direction. So this is just to show you how we come up with those detector readings, so that you can, in an exam, you can easily be able to tell the detector readings. Okay, next. High-speed electrons are incident on a metal target. The spectrum of the emitted X-ray radiation is shown in the figure here. So this is the figure. As you can see, it is an X-ray spectrum, and therefore they're telling us to explain why there is a continuous distribution of wavelengths. So in your class, you must have explained this spectrum here. You must have noted that it has three important features. We have the background radiation, we have the sharp peaks, which are superimposed on the background radiation. We call this one the line spectrum. And we have what we call the cut-off wavelength, which is the minimum wavelength corresponding to the highest energy or the maximum frequency. So explain why there is a continuous distribution of wavelengths. Why do we have a wide range of wavelengths starting from a minimum? You must have noted during the study of this part that during the production of X-rays, not all X-rays undergo the same decelerations when they collide with the target. And therefore, if they undergo different decelerations, it means the resulting energy photons are going to be different. Remember, the energy of the X-ray photons depends on the decelerations. So since we have different decelerations, we expect different photon energies. And remember, the energy of an X-ray photon is HF, which is Hc over lambda. We expect different photon energies, different photon frequencies, therefore different photon wavelengths. This is what is going to give us a distribution of wavelengths. Okay, so we are saying X-rays are produced. X-rays are produced. X-rays are produced when charged particles are accelerated. When charged particles are accelerated. When electrons hit the target, when electrons hit a target, they have a range. They have a range of decelerations. Of course, I can use acceleration and decelerations wherever I want, because after I know acceleration could be positive, but deceleration is still negative acceleration. So when electrons hit a target, they have a range of decelerations. And because they have a range of decelerations, they will also have a range of energy of photons. And thus, wavelengths, since the wavelengths depend on the decelerations, so they will have a range of wavelengths. When electrons hit a target, they have a range of decelerations. So, and we know that the energy of photons and thus wavelengths depend the energy of photons and thus wavelengths depends on the decelerations. Depend on the decelerations, hence having a range of wavelengths. hence having a range of wavelengths. So that's why we have a continuous distribution of wavelengths. Then we have to explain why there is a sharp cutoff at short wavelength. In other words, why there is lambda minimum here. Remember, lambda minimum corresponds to minimum wavelength, which corresponds to maximum frequency, which corresponds to maximum energy. Energy is equal to HF, which is Hc over lambda. Minimum wavelength, maximum frequency, maximum energy. When does an X-ray photon have maximum energy? This is when an electron gives out all its energy as a single X-ray photon. That photon will have the highest amount of energy. So we can simply say, this corresponds to the shortest wavelength, which is as a result of an electron giving up all its energy as an X-ray photon, in one collision. That is, remember, lambda minimum is going to be H C over Emax, maximum energy. So the photon will have maximum energy. In one single collision, if the electron gives out all its energy as a single X-ray photon, then the X-ray photon will have maximum energy. State what is meant by hardness of an X-ray beam. Of course, hardness is a measure of penetration power of the X-ray beam. A measure of just the penetrating power of an X-ray beam. A measure of the penetrating power or the penetration power. Penetration power of the X-ray beam. A measure of the penetration power of the X-ray beam, but know that there are two marks. So answering questions carefully is very important. This statement that it is a measure of the penetration power of the X-ray beam cannot give you 2 marks. Emphasis is very important. The greater the penetrating power, the greater the hardness, or the greater the hardness. So we can simply say greater hardness means greater penetrating power. So greater hardness means greater penetrating power. Okay. State how hardness is controlled. Of course, we mentioned that hardness is controlled by the accelerating PD. The higher the accelerating PD, the greater the hardness. So to control hardness, we just adjust the penetrating PD or the anode voltage. So adjusting the accelerating PD which is sometimes called the anode voltage. which is sometimes called the anode voltage. And the higher the anode voltage or the accelerating PD, the higher the accelerating PD, the greater the penetration power, or the greater the hardness. The higher the accelerating PD, the greater the hardness. Suggests why, when producing an X-ray image, longer wavelength X-ray radiation poses a greater hazard to health than short wavelength. Of course, long wavelength, these ones are called the soft X-rays, and the short wavelength are called the hard X-rays. Of course, the longer wavelength are less energetic, the short wavelength are more energetic. So if they are the long wavelength are less energetic, it means they are less penetrating. Therefore, they are most likely not going to contribute to the X-ray image. Therefore, they actually have, because they don't penetrate through the body, they just increase the dose which you are taking in the body, since they don't easily emerge out of the body. So we can say long wavelength radiation are more likely to be absorbed in the body. Long wavelength radiation are more likely to be absorbed in the body as they are less penetrating. As they are less penetrating, and of course they will be increasing the dose. Increasing the dose. So they are less penetrating, but they will be accumulating in the body, and they will be increasing the dose. Suggest how the hazard is minimized. How is this hazard be minimized? So we have said, or you must have heard from your class, that actually normally during the production of X-rays, the X-ray window is fitted with the X-ray window is normally fitted with an aluminium filter whose purpose is to remove or to absorb the longer wavelength X-rays, which do not serve any purpose during the production of an X-ray image, but simply increase on the dose. So an aluminium filter is placed at the X-ray window. An aluminium filter is normally placed at the X-ray window to absorb the longer wavelength X-ray radiation. Absorb the longer wavelength X-ray radiation. So that is why that is how we can minimize the hazard of these long wavelength X-rays. We just try to prevent them from reaching the body by filtering them out just at the X-ray window during the X-ray scan. The use of X-rays in medical diagnosis gives rise to an increased exposure of the patient to radiation. Explain why an aluminum filter may be placed in the X-ray beam when producing an X-ray image of a patient. So you must be thinking about this question as similar to the previous question. So we are going to simply consider this question similar to the previous question. We said an aluminum filter always absorbs the long wavelength X-rays, which do not contribute to an X-ray image, but simply increase the dose that you are taking in. So an X-ray beam is going to have both the soft and the hard X-rays. Remember, the soft X-rays are the long wavelength. They are less penetrating. When passed into the body, they just accumulate within the body without even contributing to the X-ray image. So these are supposed to be filtered out using the aluminum filter. So we can say an X-ray beam, an X-ray beam contains a range of wavelengths. An X-ray beam contains a range of wavelengths, as we saw in the spectrum. The aluminum filter the aluminum filter absorbs the long wavelengths X-rays or X-ray radiation. The long wavelength the aluminum filter absorbs the long wavelength X-ray radiation that would be absorbed by the body. That would be absorbed by the body and not contributing to the image, but simply increasing the dose. So an X-ray beam contains a wide range of wavelengths. That's why we had a continuous distribution of wavelengths. The aluminum filter absorbs the long wavelength X-ray radiation. That would be the aluminum filter absorbs the long wavelength X-ray radiation. That would be absorbed by the body and not contributing to the image, but simply they would be increasing the dose that you are taking in, which is dangerous to your body. The radiation dose received by a patient is different for a CT scan from that for a simple X-ray image. That is very true. We want to explain why. Remember, an ordinary simple X-ray image involves a single exposure. An ordinary simple X-ray image involves a single exposure. So you are exposed to X-rays just from one direction, just once, if it is a simple X-ray image. But then for a CT scan, remember, it involves several X-ray images for a single slice, and there are always many slices to be investigated. So that means the exposure is much greater. So a CT scan involves or consists of many X-ray images of a slice. So a CT scan consists of many X-ray images of a slice, and remember, there are many slices which to be investigated. So a CT scan consists of many X-ray images of a slice, and there are many slices. And there are many slices, which means there are many slices, which means there is so much greater exposure with the CT scan. So remember, to form a three-dimensional image during a CT scan, um, a series of X-ray images of a single slice are taken from different angles, and these images are always in the same plane, and therefore they are combined to form a complete two-dimensional image. Several other slices are also going to be X-rayed in a similar way, and their corresponding two-dimensional images are going to be combined all together to form a complete three-dimensional image. All this is involving X-rays from different angles and for several slices. That means the dose being taken in during a CT scan is much greater than that taken in during an ordinary simple X-ray scan. Okay. Here we have a CT model. In a model for CT scanning, a section is divided into four voxels. The pixel numbers P, Q, R, and S of the voxels are shown here. So these are the pixels P, Q, R, S. Remember, pixel is a number which just represents the intensity of the X-ray beam which goes through a specific voxel, and the voxel is a volume element. So the section is viewed from the four different directions: D1, D2, D3, and D4. The detector readings for each direction are noted here. Okay. So they have given us the background reading. Remember, this is the sum of the detector readings in any one particular direction. Determine the pixel numbers P, Q, R, and S. Okay, so I'll draw another table here as part of my working. So I will have, remember, the final detector reading, you subtract the background, divide by 3 to consider allowance for the fact that more than one view was taken. We have 61 minus 34, we divide this by 3. We have 73 minus 34, divide this by 3. 55 minus 34, divide this by 3. So you press your calculator. or you check with your calculator. For the first one, 49 minus 34 divided by 3, I think this is 5. The second one, 61 minus 34 divided by 3, I think this is 9. Then 73 minus 34, 73 minus 34 divided by 3, I think this is 13. And 55 minus 34 divided by 3, that is 7. So the answers here would be 5, 13, 9, and 7. Distinguish between an X-ray image of a body structure and a CT scan. Of course, an X-ray image, that is simplest, a two-dimensional image on a flat piece of material which does not even indicate how deep the organs are inside the body. So these are, we first look at the marks, there are 5 marks. So I think 2 will be for the first part and 3 will be for the second part. So we can say an X-ray image. This one, it's a two-dimensional what? It's a two-dimensional image which does not indicate the depth. Which does not indicate the depth of an organ in the body. It's a two-dimensional image which does not indicate the depth of an organ in the body. Then a CT scan, this one is built, remember, from several X-ray images taken from different angles to form a three-dimensional image. Remember, this one can be rotated and viewed from any angle. So this one, it is built up spelling of built. It is built up from many images of slices taken at different angles. At different angles. We know that the image is three-dimensional. The image is three-dimensional and can be rotated and viewed at different angles. So the image is three-dimensional. It can be rotated and viewed from different angles. That is for the CT scan. So here we have data. We have for a metal. We have a metal is aluminium, and the other one is copper. They have given us values of mu, which I think those are linear attenuation coefficients, copper and aluminium. A parallel X-ray beam is incident on a copper filter, as shown here. The intensity of the incident beam is I naught on a copper filter. Calculate the thickness of copper to reduce the intensity of the emergent beam to this one here. So assuming the X-ray, because this was a parallel X-ray beam. So if the intensity, the reduction in the intensity is exponential, then we can say intensity, I call this I1, is going to be equal to I naught e power negative mu x. So we want the emergent beam to have intensity 0.25 I naught. So I'll just substitute 0.25 I naught should be equal to I naught e power negative mu times x. And therefore it means we just solve this. I naught cancels, we introduce ln. So ln of 0.25 is going to be equal to, when I find ln of mu of e power negative mu x, I only remain with the power. And remember, mu for copper was given the top table, which is 0.69. So I'll just substitute here. So this will be negative 0.69 times x. I did not change the units of mu, it is per millimeter. Therefore, it means here it is also going to be in millimeters. So we simply say that x is going to be equal to 0, sorry, not 0. X is going to be 2.0 in millimeters. So the answer here is going to be 2.0 in millimeters. Avoid writing answers which are not exact to less than two significant figures. There should be two significant figures and above. That's why you see I've added here 0.0. An aluminium filter of thickness 2.4 millimeters is now placed in the X-ray beam. Remember, the aluminium filter removes the less penetrating or less energetic X-rays or the soft X-rays. Calculate the fraction of the incident intensity that emerges after passing through the two filters. After passing through the two filters. So we have an aluminium filter and a copper filter. So for aluminium, I'll call this one I2. For aluminium, I'll call this one I2. Remember, they have put an aluminium filter here before it reaches the copper, so it first has to go through aluminium, then the copper. So for aluminium, is it after that? No. An aluminium filter of thickness is now placed in the X-ray beam together with the copper filter in Roman 1. Okay, it's only that it's not showing where it is placed, but let's say it is placed maybe after copper. Let's place this after copper. So an aluminium filter is placed after copper. So it means what is incident on the aluminium is what is leaving copper. So I2 is going to be equal to I1 e power negative mu times x. Okay, so if we make substitutions, so we shall have that because we want the fraction of the incident intensity that emerges after passing through the two. So I will simply first of all find this one. So this is going to be I2 is equal to I1 e power negative mu is for aluminium is 0.46 and the thickness is given as 2.4. So I will say times 2.4. So this was per millimeter, 2.4 is per meter, is millimeter, so I don't convert. So this gives me I2 as pressing my calculator here, e power negative 0.46, there's a negative here, e power negative 0.46 times 2.4. So from my calculator, I'm getting I2 as 0.33 times I1. Okay, but I want the fraction of the incident intensity that emerges after passing through. So I have to remove I1 and I put there I0. Remember from the previous part, I naught, I1 is 0.25 I naught. So it means I2 is going to be 0.33 times 0.25 I naught. So the fraction is I2 over I naught as required, which is the product of 0.33 times 0.25. And this gives me 0.083 to two significant figures. Express your answer in Roman 2 as a gain in decibels. Although gain is removed from the syllabus, especially the unit of decibels, was very common under communication, that is attenuation in decibels, we can still find this. Of course, decibels just simply means 10 log of that fraction. So gain in decibels is simply the same as 10 log. This will be now 10 log of I2 over I naught, which is simply going to be 10 log of the fraction that we got as 0.083 in decibels. And this is, I think, from my calculator, so this is negative 10.8, which is approximately negative 11 decibels. Decibels is 10 log of that fraction, but it was common in a unit called communication, especially attenuation of signals. Okay, next. In computed tomography, that is CT scanning, it is necessary to take a series of X-ray images. Outline briefly the principles of CT scanning. Those are 4 marks. The principles of CT scanning. Remember, a series of X-ray images are taken. These are always taken from different angles and they're in the same plane. They are combined to give two-dimensional images of one slice. The procedure is repeated for all other slices, and then all the successive two-dimensional images are combined to form a complete three-dimensional image of the whole object, which is the tomography or the cross-section. Okay, so we are going to say that a series of X-ray images taken from different angles are obtained. A series of X-ray images taken from different A series of X-ray images taken from different angles are obtained for one slice. A series of X-ray images taken from different angles are obtained for just one slice. Taken for one slice of the organ being investigated. Okay, all the images for this slice are going to be in the same plane. All these images are in the same plane. All the images are in the same plane. So the images are combined The images are combined to give a complete two-dimensional image. A complete two-dimensional image of the slice. So all the images of one slice are combined to give a complete two-dimensional image of that particular slice. Then more slices are imaged similarly. More slices are going to be imaged similarly. Now what remains is combining all the two-dimensional images by a high-power computer to build up a three-dimensional image. So we simply say the images of successive slices. The images of successive slices are then combined using a high power computer to build up a 3D image, which can be of course a three-dimensional image of the entire structure, which can be rotated and viewed from various angles. So the CT scan is easy to describe as long as you know that several slices are going to be imaged using these X-rays, and their images are going to be combined to form a complete two-dimensional image. Then other slices are going to be investigated in the same way, and the two-dimensional images are going to be combined using a high-power computer to form a three-dimensional image, which can be rotated and viewed from any angle as required. Okay. A student creates a model for CT scanning. The section is divided into 4 voxels with the pixels A, B, C, and D, as shown here. The section is viewed from 4 different directions: V1, V2, V3, and V4. V1, V2, V3, and V4, that is from the bottom. The section is viewed from those directions. The background count is 26. Remember, the background count is the sum of the detector readings in any one direction. Determine the pixel numbers A, B, C, D, A, B, C, and D. So we have to move backwards to the original pixels A, B, C, D. So I will draw a simple table. So 47, I will subtract the background and divide this by 3. 3 more views have been taken. 59, I will subtract 26, I will divide this by 3. 44, I will subtract 26 and divide this by 3. And 32, I will subtract 26 and divide this by 3. So from your calculator, so from my calculator, I have 7, I have 6 here, and I have 11 here, and I have 2 there. That should be the easiest process. These 3 marks are supposed to be very free. 3 marks are supposed to be free. State what is meant by hardness of an X-ray beam. I think at this point we now know what hardness is. The penetration power or penetration of a beam of X-ray. So that is the penetration power. Penetration power of an X-ray beam. Greater hardness, of course, the greater the hardness, the greater the penetration power, or we simply say greater hardness. Greater hardness means greater penetration. Greater hardness means greater penetration. Of course, that means high frequency. How hardness of an X-ray beam can from an X-ray tube is increased, not controlled, but increased. If we want a higher hardness, we have to increase the accelerating PD. So this is achieved by increasing the accelerating PD. Increasing the accelerating PD, or you would simply say using a greater PD between the anode and cathode. Using a greater PD between anode and cathode. Okay. The same parallel beam of X-ray radiation is incident separately on samples of bone and of muscle. Data for the thickness X of the samples of bone and of muscle together with the linear attenuation coefficients mu of the radiation in bone and muscle are given in the table here. So we have X thicknesses, we have the mu values for bone and muscle. Determine the ratio intensity transmitted through bone over intensity transmitted through muscle. I think that is easy. Intensity transmitted through bone over intensity transmitted through muscle. They told us that the beam is passed separately. It is passed separately. So that means the incident intensity is the same. So intensity, remember, is going to be equal to I naught e power negative mu x. So the ratio is going to simply be, remember, I naught is the same. So when I divide it, it will cancel out. What is changing is mu and x. So I'll simply say the ratio will be e power negative mu for bone, and mu for bone is 2.9. It is in per centimeter, but x is also in centimeter, so this will be times x, which is 1.5. I don't change these units. So this is mu for, that is E for bone, divided by E for muscle, where mu is, so this will be negative 0.9. 0.95 times the thickness, which is 4.0. So this is, of course, mathematically, I think this is e power negative. This is 2.9. You subtract the powers. So this becomes e power negative 0.55. When I press my calculator, so from my calculator, I'm getting this as 0.58 to two significant figures. 0.58 to two significant figures. State with reference to X-ray image what is meant by sharpness. Of course, sharpness refers to the ease with which the boundaries are determined, or the ease with which the edges between organs can be clearly distinguished. That is sharpness. So we shall say sharpness is the degree to which the edges or the boundaries between organs can be clearly distinguished. Can be clearly distinguished. Degree to which the edges or the boundaries between organs can clearly be distinguished or outlined. That's what we call sharpness. Describe briefly two factors that affect the sharpness of the X-ray image. The question says describe briefly. You don't just state. Of course, the sharpness is going to be affected by the size or the area of the X-ray source, which is the target anode. So we can talk about the size or the area of the X-ray source, which is specifically the target anode. The size or the area of the target anode affects the sharpness. We know that a smaller area of the target anode improves sharpness. A smaller area of the target anode improves sharpness. Number two, apart from the size or the area of the target anode, apart from the area or the size of the target anode, I think target, this is A, sharpness can also be affected by scattering of the X-ray beam. Scattering of the X-ray beam. Scattering of the X-ray beam also affects sharpness. This can be reduced by using a red grid, of course, which we call the anti-scatter screen. So this is reduced. This is reduced by using a LED grid. To absorb the scattered photons. So sharpness is also affected by scattering of the X-ray beam, but this can be reduced using a LED grid, which we call the anti-scatter screen. Sharpness is also affected by the pixel size. Pixel size. Of course, the smaller the pixel size, the better the sharpness. Okay, so that is sharpness, but the most important ones are the first two. Area of the target anode, scattering of the X-ray beam. An X-ray image is taken of the skull of a patient. Another patient has a CT scan of his head. By reference to the formation of the image in each case suggests why the exposure to radiation differs between the two imaging techniques. Of course, the X-ray image involves a single exposure. The X-ray image involves a single exposure. The X-ray image involves a single exposure, but not with a CT scan. For a CT scan, there is exposure of a slice from many angles from many different angles. Remember, this is repeated for several other slices, which is repeated for several other slices, for many different slices. Therefore, the CT scan involves much greater exposure. The CT scan involves much greater exposure. Okay, next. A simple section through a body consists of 4 voxels. Those are volume elements, as illustrated here. An X-ray image of the section is obtained by viewing along each of the directions as shown in the figure 10.1. Okay, we can see the views. The detector readings for each direction of view are summed up to give the pattern of the readings as shown here. For any one direction, the total of the detector readings is 16. So we say this is going to be the background intensity, the sum of the detector readings in any one direction. For the pattern of the readings in figure 10.2, state the magnitude of the background radiation. Of course, you should now be able to know that the background radiation is 16. On the figure, mark the pattern of the pixels for the 4 voxel section. So you want to put the figures to put the pattern of the readings on this figure here. So you can first of all think about it and see if you'll come up with the same values as I would. Okay, perhaps you have come up with the same values, but just for completeness, let me show you, remind you of the working. So I will redraw the detector readings. We have 25, I subtract the background, I divide by 3. I have 22 minus the background, divide by 3. 34 minus the background, divide by 3. 31 minus the background, divide by 3. So you must have got the following values. For the first one, 25 minus 16 divided by 3. I think that is 9 over 3, which is actually 3. So you must have put there 3. 22 minus 16 divided by 3. I think that is 6 over 3, which is giving us 2. 34 minus 16 over 3. I think that is 18 over 3, which gives us 6. And 31 minus 16 over 3. I think that is 15, which gives us 5. So you must have filled that there are those vexels with those numbers or those pixels. Okay. High energy electrons collide with the metal target, producing X-ray photons. The variation with the wavelength of the intensity of X-ray beam is illustrated here. So we have that illustration. Explain why there is a continuous distribution of wavelengths. Now we have answered a similar question. It should now be easy for us to explain why there is a continuous distribution of wavelengths. Remember we said X-ray photons are produced when electrons are suddenly decelerated. So X-ray photons are produced when electrons are suddenly decelerated. Suddenly, of course, and rapidly. X-ray photons are produced when electrons are suddenly decelerated, and a range of decelerations occur in the target. A range. I think a range is there are 2 words here. A range of decelerations occur in the target. A range of decelerations occur in the target. Remember, the energy of the X-ray photons depends on these decelerations. Energy of X-ray photons depends on these decelerations. Hence, a continuous distribution of wavelengths. A continuous distribution of wavelengths. Okay, so that is why we have a continuous background, then a sharp cut off at short wavelength. This corresponds, of course, this is the shortest wavelength. It's the shortest wavelength which corresponds to an electron which gives all its energy as one photon. As one X-ray photon in a single collision. The shortest wavelength is the shortest wavelength which corresponds to an electron which gives up all its energy as one X-ray photon in a single collision. Then we have a series of peaks superimposed on the continuous distribution. Remember, those ones are as a result of electron de-excitation. Electrons from the cathode penetrate deeper into the target and knock out other electrons into higher energy levels. The atoms are said to be excited. On de-excitation, these electrons re-emit the energy in form of X-ray photons. So in other words, since they have given us only one mark, this one results from the excitation of orbital electrons in the atoms of the metal target. Results from de-excitation. From the excitation of orbital electrons in atoms of the metal target. When the atoms of the metal target undergo the excitation, they re-emit X-ray photons. In the X-ray imaging of body structures, long wavelength photons are frequently filtered out of the X-ray beam. State how this filtering is achieved. That is achieved by using an aluminium filter. Aluminium filter is placed. An aluminium filter is placed at the X-ray window. At the X-ray window of the tube. An aluminium filter is placed at the X-ray window of the tube. Suggests the reason for this filtering. Of course, we know why we should filter them. Those long wavelengths, they are less penetrating. They do not pass through the body, so they do not contribute the image, but rather increase the dose. So the long wavelength X-rays do not pass through the body. They do not pass through the body, so they do not contribute to the image. So they do not contribute to the image, but rather increase the dose. But they would rather increase the dose. In an X-ray tube, the hardness of an X-ray beam may be controlled. State what is meant by hardness. Now we know what hardness is. That is the penetration power of an X-ray beam. Penetration power of an X-ray beam. Penetration power of an X-ray beam, and remember, the higher the penetration power, the greater the hardness, or the greater the hardness, the higher the penetrating power. The greater the hardness, the higher the penetrating power. State how hardness of the beam may be decreased. Now this time we are decreasing. The other time it was increasing, where we increase the accelerating PD. So this time they want their specificities to decrease. So here we just decrease the accelerating PD. So decrease the accelerating PD. Or you can simply say decrease the voltage between the cathode and anode. Decrease the voltage between the cathode and the anode. Okay. State one advantage and one disadvantage of producing a CT scan image of a person rather than a standard X-ray image. One advantage of a CT scan, the image gives details of depth and it is three-dimensional, which can be viewed from many angles. I think that is the major advantage. So advantage, the image gives depth of structures in the body. So the image gives depth since it is 3D. It is three-dimensional and it can be viewed from any angle. So that is the major advantage of the CT scan. Of course, the disadvantage, there is too much exposure to X-rays. It involves greater exposure. It involves greater exposure to X-rays. It involves greater exposure to X-rays, so more risk. They are more risk, or so there is more risk of. It's more risk to more risk to health. There's more risk to health. Not forgetting that it is even more expensive. It is even more expensive. Of course, another disadvantage, the person must remain stationary. That means it is not suitable for babies. The person must remain stationary. So not suitable. So it's not suitable for babies. Because the person must remain stationary, you can't tell a baby to remain stationary. So it's not suitable for babies. But the major important disadvantages are it involving greater exposure to X-rays. So there is more risk to health. You can talk about it being expensive and the person must remain stationary, so it's not suitable for babies. Distinguish between sharpness and contrast. Now we know what sharpness is. That one relates to boundaries, and contrast relates to the degree of blackening. So sharpness, that is the ease with which the edges call them boundaries of structures can be distinguished or seen. So that is sharpness, the ease with which the boundaries between structures or the boundaries of structures can be distinguished or seen or outlined. That is sharpness. Then contrast, that is the difference in the degree of blackening. Difference in the degree of blackening. Difference in the degree of blackening. Degree of blackening between structures. Difference in the degree of blackening between structures due to their of course this is due to their absorption properties of X-rays. Due to their absorption properties of X-rays. Due to their absorption properties of X-rays. That is contrast. Difference in the degree of blackening between structures due to their absorption properties of X-rays. Of course, we said bone and muscle, there is a good contrast because bone is a good absorbent or has better absorption properties of X-rays compared to its surrounding. Okay. The student investigates the absorption of X-ray radiation in a model arm. A cross-section of the model arm is shown here. So you notice that this one goes through the bone, this one goes through muscle. Of course, you will notice that this part here, this thickness is going to be 2 centimeters. This thickness is also going to be 2 centimeters. Because bone is 4 centimeters, but the width here is 8 centimeters. Parallel X-ray beams are directed along the line MM and along the line BB. The linear absorption coefficients of the muscle and of the bone are given here. We have 0.2 and 1 and 12 per centimeter. Calculate the ratio intensity of the emergent X-ray beam from the model over the intensity of the incident X-ray beam on the model for a parallel beam of X-ray for a parallel X-ray beam directed along the line MM. So MM is only through the muscle. So that one is very easy. We just do it once. Remember, intensity transmitted I is equal to I naught e power negative mu x. So we want I over I naught, which is going to be e power negative. This is through muscle alone. So this will be negative 0.20 times the thickness, which is 8 centimeters. Because I didn't change 0.2 from per centimeter to meters, I will also not change the thickness. I'll just write 8 centimeters. The units cancel out. From my calculator, here, I'm getting this as 0.202 significant figures. Then we want along BB. Along BB. This is going to be a long process, but I'll try to simplify it. So if we say the intensity coming here is I naught, what is incident here is I1. I1 is the same intensity which is just enters the bone. And let's say what reaches the other end of the bone is I2. I2 is the same intensity which just leaves the bone. And let's say what reaches the other side is I3. So we want I3 over I naught. That's what we are going to do. We want I3 over I naught. So to begin with, let's find I1 which arrives just on the bone. So using I equals to I naught e power negative mu x. So we shall see that I1 is going to be I naught e power negative the through muscle, because before it reaches bones it is going through muscle, so that is negative 0.2. The thickness it passes through before it reaches bone is 2 centimeters. So this is giving us this value as let me check my calculator. 0. Okay, I'll just leave it the way it is like that. Then let's check I2. Remember, I2 is what arrives on the other end of the bone. I2 is what arrives on the other end of the bone. Let's say I1 is just leaving the boundary of the bone, and I2 reaches the other end of the bone. So I2 will also be equal to now I1, because I1 is incident. Then e power negative. The coefficient of bone is is actually 12, so it will be negative 12 times the thickness, which is 4. Then now let's say I2 just leaves the bone and again enters the muscle. So it means I3 is what arrives on the other end of the muscle, and I2 is what is incident. This will be e power negative. Muscle is 0.2 times thickness, which is also again 2. Now just do back substitution. So I3 is going to be equal to I2 times this, and I2 is I1 times that, and I1 is I naught times that. So when we do back substitution, we shall have I naught e power negative 0.2 times 2 times remember I naught e power, that is I1, but there is e power negative 12 times 4, and e power negative 12 times 4 times I1 is also I2, so I'll say times e power negative 0.2 times again 2. So I'm just doing back substitution. You can even press the calculators and get each of those values, and then you do back substitution. So when I do back substitution here, I now have that I3 divided by I naught is going to be the product of all these three, which when I press my calculator, from my calculator it is giving me 6.4 times 10 power negative 22. Of course, this is approximately 0. So you can write 6.4 times 10 power negative 22, or if you want, you can write approximately 0. Okay, so that is through bone. State whether your answer in B would indicate that the X-ray image is sharp. So of course we cannot tell the sharpness by looking at the fraction of ultrasound of X-ray beam which has gone through. So there is no information about sharpness, so we can simply say sharpness is unknown. The sharpness is unknown because the sharpness cannot be obtained or compared by looking at the intensity which goes through. Then good contrast, I think good contrast is good because if there is soft tissue, you see the intensity going through is very high, the ratio is very high. And when there is bone, you see the ratio is very small. So there's a high difference in the degree to which blackening is going to be caused. So here we shall say the contrast is good, or you just say yes. State whether the answer in B indicates that the X-ray image has good sharpness. So here it is yes. If you want to give a reason, you notice that IMM is much greater than I through BB. So there is very good contrast. Okay. Electrons are accelerated through a potential difference. Electrons are accelerated through a potential difference of 15 kilovolts. The electrons collide with the metal target and a spectrum of X-rays is produced. Explain why a continuous spectrum of energies of X-ray photons is produced. Now we know why we have a continuous spectrum of X-rays. So what does the continuous spectrum stand for? Electrons are going to be decelerated on hitting the metal target, so the X-ray photons are produced. Of course, they undergo different decelerations, so they will have a wide range of energies since the energy of the X-ray photons depends on these decelerations. The X-ray photons will have different wavelengths. So electrons are decelerated. Electrons are decelerated on hitting the metal target. So that X-ray photons are produced. The electrons have a range of decelerations in the target. The electrons have a range of decelerations in the target, and the photon energies depends on the magnitude of decelerations. The photon energies or wavelengths depend on the magnitude of decelerations. Thus, a wide range. So there will be a range of wavelengths. The photon energies depend on these decelerations. So there will be a range of wavelengths since electrons undergo a wide range of decelerations. Calculate the wavelength of the highest energy X-ray photon produced. Remember, all the electron gives out all its energy as a single X-ray photon. The energy of the electron is given by E times V. The energy of the photon is given by HF, which is Hc over wavelength. So the wavelength is going to be Hc divided by E times V. So we substitute Planck's constant, that is 6.63 times 10 power negative 34, 3 times 10 power 8, divided by 1.6 times 10 power negative 19, then times 1000, it was given as 15K PD. So that is 15,000. So press my calculator. So from my calculator, I have 8.3 times 10 power 11 meters. Okay, a beam of X-rays has an initial intensity I naught. The beam is directed into some body tissue after passing through the thickness X of the tissue. The intensity is I. The graph in the figure shows the variation with X of I of ln of I over I naught. So this is a graph of ln of I over I naught against the thickness X, Determine the linear attenuation or absorption coefficient mu for this beam of X-rays in the tissue. So we want to determine mu. Remember, we know that I naught is equal to intensity transmitted. The intensity transmitted I is equal to I naught e power negative mu times X. So I over I naught is equal to e power negative mu times X. Introduce ln both sides, the other side also ln. So you have ln of I over I naught is equal to the other side, this will be negative mu times X. We have plotted the graph of ln of I over I naught against X, so you can see that the gradient is equal to negative mu. So gradient is equal to negative mu. If you compare with y is equal to mx plus c. The gradient is equal to negative mu, so we just find the gradient. So I'll take, I can even take the whole, so this is going to be 1, 2, 3. The scale here is 0.2 divided by 5. 0.2 divided by 5, that is 0.04. So this is going to be negative 2.28. It is starting from the origin, so I'll say negative. The gradient equals to negative 2.28 minus 0, that is on the y-axis. On the x-axis, it is at the extreme, so that is 11 minus 0. This is 11. It is 11 minus 0. So this is 11 minus 0. So that is the gradient. and your answer here is going to be negative. So this is negative 0.2072. So negative mu is equal to negative 0.2072. Therefore, mu is going to be 0.21 to two significant figures. Okay. Determine the thickness of tissue. Determine the thickness of tissue that the X-ray beam must pass through so that the intensity of the beam is reduced to 5.0% of its initial value. So remember, intensity transmitted I is equal to I naught e power negative mu x. We want I naught to be 55.0%. That means the intensity transmitted is going to be 0.05 times I naught, equaling to I naught e power negative. Mu has been given as, the value of mu is given as, where is mu? Oh, we have calculated the mu, 0.21. So this will be negative 0.21 times the thickness x. So mu naught, I naught has cancelled. You introduce natural log. So you have ln of 0.05 is equal to negative 0.21 times x. So what is x? So x is going to be ln of 0.05 divided by negative 0.21. Press the calculator. So this is approximately 14 in centimeters, two significant figures. Note that I didn't change the units, so this is still remaining as 14 centimeters. State how in a modern X-ray tube the intensity of the X-ray beam and its hardness are controlled, not increased, not decreased. So to control the intensity, remember the intensity depends on the filament current or the tube current, or sometimes we call the cathode, the PD across the cathode filament. So we vary the filament current, or you can call it the PD across the cathode filament. Remember, the number of electrons depends on the filament current. And the number of electrons are going to determine the number of X-ray photons emitted. And the number of X-ray photons emitted, that is now the intensity. Then for hardness is controlled by the accelerating PD or the anode voltage. So we vary the accelerating PD. Vary the accelerating PD to control the hardness. We vary the accelerating PD. A model of a limb consists of soft tissue and bone as illustrated here. The thickness is 3 from one end to another end. That means this is going to be 3. The other side is also going to be approximately 3 centimeters. The soft tissue has thickness 9 centimeters. The bone with the soft tissue has thickness 3 centimeters. Data for the linear attenuation coefficient mu of X-rays in soft tissue and in bone are shown in the table. So you see soft tissue and we see bone, that is the attenuation coefficients. A parallel beam of X-rays of intensity I naught is incident normally on the model. Calculate in terms of I naught the transmitted intensity IS through soft tissue alone. So we want IS through soft tissue. So that is very easy. IS is equal to I naught e power negative mu times x. So we want the transmitted intensity IS through soft tissue. So IS is going to be equal to I naught e power negative. Mu for soft tissue was 0.92, so that would be negative 0.92. and the thickness of soft tissue is 9 centimeters, 9.0. So we now press our calculator. So from our calculator, we are getting 2.5 times 10 power negative 4. That is through the soft tissue alone. Then that one intensity IC through soft tissue and bone. Now that one is similar to the previous question we have taken. Let's say what arrives here is I naught, what leaves here is I naught. What arrives here is I1 and it's what leaves. What arrives on the other side of the bone is I2 and it's what leaves. And what arrives the other side is IC. So we shall find I1 in terms of I naught. We shall find I2 in terms of I1. And we shall find IC over I2. So that we now have to do back substitution and we find the intensity through the intensity IC through soft tissue and bone. So we have already seen that let's say I1 is what just arrives at the bone. So I1 is going to be, I1 is going to be I naught e power, because it is passing through soft tissue, that would be negative 0.92 times the thickness, which is 3, before it reaches bone. Then now I1 is incident on the bone and it's what leaves the bone. What arrives to the other end of the bone is I2. So I2 is going to be I1 e power. Bone has negative, this will be negative 2.9, that is mu for bone. Thickness of bone is 3. Then I2 just leaves the bone and again re-enters soft tissue. So IC, which arrives to the other end of soft tissue, is equal to I2 e power negative. We are now in soft tissue again. This will be 0.92 times 3. So we now want IC in terms of I naught. So we do back substitution. Where there is I2, I put that one. Where there is I1, I put the first one. So you notice that this will be I naught e power negative 0.92 times 3 times e power negative 2.9 times 3 times e power again negative 0.92 times 3, just doing back substitution. So this is giving me from my calculator so from my calculator, I'm getting IC as being equal to 6.7 times 10 power negative 7 times I naught. So the answer here is 6.7 times 10 power negative 7. By reference to your answer in B, suggest with a reason whether good contrast on an X-ray image would be obtained. So compare when it goes through, when there is bone, and compare when it goes through only soft tissue. I think this is much smaller than the other one, so we can say there is good contrast. So IS is much greater than I, which goes through C. So the contrast is good. But we don't have any information about the sharpness, so we can't talk about sharpness there. Electrons are accelerated through a potential difference of 100 kilovolts. They are then incident on a metal target. They decelerate and X-ray photons are emitted. Calculate the maximum possible frequency of the emitted X-ray photons. So we know that the electron gives out all its energy, which is E times accelerated PD as X-ray photon HF. So F maximum is going to be EV, which is 1.6 times 10 power negative 19, that is the charge of an electron, times 100 times 10 power 3, that is the PD, divided by H, which is 6.63 times 10 power negative 34. So from my calculator, From my calculator, I have 2.41 times 10 power 19 hertz. Explain why an aluminium filter may be placed in the X-ray beam when producing an X-ray image. So this is now a common question. We now know that the X-ray beam contains many wavelengths, a range of wavelengths. So an X-ray beam contains many wavelengths. Contains many wavelengths. The aluminium filter absorbs. The aluminium filter absorbs the long wavelength low energy long wavelength low energy X-rays which do not contribute to the image, but rather increase the dose taken in, which can cause harm, or which has a healthy hazard. Okay, the linear attenuation (absorption coefficients mu for X-rays in bone, blood, and muscle are given in the table here. A beam of these X-rays is incident on a person. Calculate the percentage of the intensity of the X-ray beam that has been absorbed after passing through 0.8 centimeters of blood. The percentage of the intensity of the X-ray beam that has been absorbed after passing through 0.8 centimeters of blood. So intensity transmitted is equal to I naught e power negative mu times x. Negative mu times x. So we want I over I naught. That is the percentage. We are going to multiply this by 100. So this is going to be E. So this is what is transmitted. So E power negative 0.4. That is blood, 0.23 times the thickness 0.80, and so what has been transmitted from my calculator is 0.83. That has been transmitted. That means what has been absorbed, because we want the fraction that has been absorbed. So fraction absorbed is going to be 1 minus 0.83, which is, I think this is 0.17. And as a percentage, multiply this one by 100. That is 17%. So this is 17%. In an X-ray image, white regions show greater absorption of X-rays than dark regions. State and explain the difference between the X-ray image of bone compared to that of muscle. Of course, we know bone attenuates X-rays to a greater extent compared to muscle. So bone is going to appear white, muscle is going to appear darker. So we shall simply say bone is seen as lighter. Bone is seen as lighter or white. Or white. And muscle appears darker. This is because bone has, when you look at the table above, bone has a higher value of mu. Bone has a higher value of mu. Bone has a higher mu value, so absorbs more X-rays. So absorbs more X-rays, while muscle has a lower mu, so transmits more. So because bone has a higher value of mu, it will absorb more X-rays, while muscle has a lower mu or a lower value of mu, so it will transmit more X-rays. So lastly, for this video, for part 2, the linear attenuation or absorption coefficient for a parallel beam of ultrasound waves in air is 1.2 per centimeter. The parallel beam passes through a layer of air of thickness 3.5 centimeters. Calculate intensity of the beam after passing through the layer of air of the intensity of the beam entering the layer of air. So intensity transmitted is equal to the incident intensity e power negative mu times x. So I over I naught is what we want to find. So this will be e power negative. Mu is 1.2, it is per centimeter. Thickness is 3.5 in centimeters. I don't convert the units, they will cancel out. And this gives me um, so this gives me 0.015. That is the fraction. If we want the fraction in decibels, so the ratio in decibels is simply, remember I said decibels, that is 10 log. So that would be 10 log of 0.015, which is equal to, so this would be negative 18 decibels. So that is the fraction. Let's hang up here for this. For this, we shall stop. We have stopped on page 57. The last part will start from there. So let us have a good day. Thank you.